Okay, we're going to do the walkthrough for the partial pressure of gases POGIL. So we're looking at a stop sign after number 5. So you're going to do the first 5 problems, and then you're going to come back, unpause the video, and watch this section of the video. Okay, so model 1, it says, number 1, what do all 3 tanks have in common? Tank A, Tank B, and Tank C. And when you look at the table of things they have there, all 3 tanks are have the same volume. They have 10 liters worth of space inside of them, and all 3 tanks are at the same temperature. So volume is 10 liters, or 10.00 liters, and temperature is 298 Kelvin for all 3. 2. Determine the moles of oxygen gas and the moles of nitrogen for each tank in Model 1 and enter those values. So each of those little pairs is 0.1 mole. So they say that an oxygen molecule, or the drawing anyway of an oxygen molecule, is worth 0.1 moles of oxygen. So in tank A, we're entering them in the table. I'll just put them here. Tank A, moles of O2 would be 3 times 0.1, or 0.30 moles of O2. And tank B had 4 of those, so 0.40 moles of N2. And tank C should have gosh, let me see if I draw that better. It's the exact same, they're just combined, so 0.4 moles of N2 and 0.3 moles of O2. Alright, that should be number 2. 3, use the ideal gas law to calculate the pressure of oxygen in tank A and enter that into the table. Okay, let's do some math here. Get my calculator ready. So, we have in tank A, so we're solving this equation, PV equals nRT. For pressure. Tank A, pressure is what we're looking for. Volume is 10 liters. Okay, equal to number of moles, which we said is 0.30 moles, times R times temperature is 298 Kelvin. Notice we're in Kelvin, liters, and moles, so we can use an R of 0.0821, and that will give us the pressure in atmospheres. So that's liter atmospheres per Kelvin mole. So let's see what we can't do here. Pressure is going to be equal in tank A to 0.30 times 0.0821 times 298, and we're going to divide that by 10. I'll do that on my calculator here. I've got 0.3 times 0.0821 times 298 divided by 10, and I get 0.734. That's too many sig figs. We'll round that to 0.73 atmospheres. Alright, 0.73 atmospheres in tank A. We'll do the same thing for tank B, but plugging in this in different values. So the pressure in tank B times 10 liters, because they're all the same, equals, it's 298 Kelvin over here. And, oh, did they ask for tank B? Yes, so I'm doing number 4 now. Okay. 298 Kelvin. And in this case, it's 0.4 moles. And we're going to use that 0.0821 here. And to get rid of the 10, I'm just going to divide by 10 on both sides. So let's do that in the calculator. So 0.4 times 0.0821 times 298 divided by 10. 10, and I get something like 0.978, which is about 0.98. So equal to about 0.98 atmospheres. Makes sense. All other things being equal, if you have more moles of gas, you should have a higher pressure. So we have more pressure in 4 than in 3, or in B than in A. Okay, going on to 5. All right. Consider the total pressure in tank C, which they give us. Did they give us that? Doesn't look like they do. All right. Consider the total pressure in tank C, propose an explanation for the pressure in tank C, and be prepared to share your reasoning. Well, here's my idea. I've got 7 molecules of gas. Some of them are oxygen, some of them are nitrogen. But every time an oxygen molecule hits the wall, it creates pressure. Every time a nitrogen molecule hits the wall, it creates pressure. Now, obviously, the pressure it creates depends on how frequently they hit and how fast they're moving. So the pressure that they create can be based, again, how fast they're moving or how much space they take. And we're not changing the space. So each molecule, each of those 7 molecules, has the same space to bounce around in as each of the other 7 molecules. And each molecule, we know, also are not changing the temperature. All the molecules are at 298 Kelvin for both samples. So the pressures can basically be added up. In other words, if I have 0.3 moles of nitrogen or of oxygen and 0.4 moles of nitrogen, it's exactly like 0.7 moles of one or the other, because each individual gas particle is hitting with the same speed and frequency. That's assuming that there's not a huge difference between a nitrogen molecule and an oxygen molecule. Now, we are talking about ideal gases, and in ideal gases, we assume that each gas is pretty much going to behave or move the same way as each other gas particle out there. So I'm going to pretend this is exactly like saying there's let's go back here, 0.7 moles of gas, regardless of what type of gas that is. And I should be able to just add these pressures together, 0.73 atmospheres and 0.98 atmospheres. So I'm going to guess 0.73 atmospheres plus 0.98 atmospheres would give me a total pressure of something like 1.71 atmospheres. I think that's going to be pretty accurate. And I can make that assumption because I know that the gases, all the particles, whether they're nitrogen or oxygen, occupy the same, are inside the same volume container and are at the same temperature. That's my reasoning. All right. So you're going to then read this and then go on until you hit problem. Where's the next stop sign? Is there not another stop sign? Did they forget to put another one in? I do not see another stop sign. We're going to go till problem 10. So 6 through 10 is your next stage. And then come back and watch the video. Okay, you should have completed problems all the way up to number 10. If not, go back and finish those now. So the read this says, consider a single oxygen gas molecule. From its perspective, nothing changed when it moved from tank A to tank C. The volume available to move in is still 10 liters. The temperature is still 298 K. It will still hit the sides of the tank just as often and just as hard. And we're combining it with nitrogen. We assume that nitrogen is also very small. And so the pressure of oxygen is going to be the same from the oxygen, and the pressure from the nitrogen should be the same. So we'll call it a partial pressure, is what they're going to start saying. All right, enter the partial pressure values for oxygen and nitrogen in tank C. Partial meaning just how much did the oxygen contribute? Well, oxygen was contributing 0.78 atmospheres when he was by himself in tank A. So if we take the exact same 0.3 moles of oxygen and put them into tank C, which is the same size and same temperature, we would expect it to also produce 0.78 atmospheres of pressure from just the oxygen. So we will say that is the pressure of O2 once it gets transferred into the tank C. When we take the nitrogen used to have 0.98 atmospheres. I think I did that wrong. I think it was 0.73. Let me change that. 0.73 was the oxygen. Okay, nitrogen in tank B had a pressure of 0.98 atmospheres. If we just transfer all that nitrogen into tank C, we would expect it to still have 0.98 atmospheres of pressure because it's pushing on a same size tank at the same temperature. So pressure of nitrogen there will be 0.98. So I'm going to call that the pressure of N2. Alright, so those are the partial pressures of O2 and N2 that would exist in tank C at the same time. 7, key idea. Ooh, let's make sure we know this one. Write a mathematical equation to show the relationship between the partial pressures of oxygen and nitrogen and the total pressure. So here we go. The pressure of oxygen, when I add it to the pressure of nitrogen, should be the total pressure because they're both pushing from the inside of tank C. So tank C is going to feel all the oxygens hit it. It's also going to feel all the nitrogens hit it. That's the pressure. And then 8, write with your group, write a statement describing how combining the gases at constant temperature and volume affected the pressure of each gas. No change. The pressure of oxygen didn't change when I moved it to the new tank. The pressure of nitrogen didn't change. They were 0.73 and 0.98 respectively before, and those were the same values that they had when we put them in the new tank. It just so happened there were other things in the tank with them also exerting their own pressures. So the assumption we're making here is that the nitrogen and oxygen do not interfere with each other when we put them into the same tank, which, again, is an assumption based on the idea of an ideal gas. Ideally, that doesn't happen. Realistically, there is some interaction, but as long as it's relatively small. For now, let's assume it's relatively small. Read this. Dalton's law of partial pressures is just like we said. So the actual equation for partial pressures is that all of the gases adding up inside of a container, that's the total pressure, should equal each individual gas. So we'll say gas 1 plus gas 2 plus ... until you get however many gases there are. Pn, etc. for n number of gases. Okay. So that's 8. Let's go on to 9. Alright, a chemistry student uses a pressurized tank at 0.2 atmospheres of a gas Z, and he adds that to tank C in Model 1. What is the partial pressure of the component gases after gas C? So now let's think about it. We have a tank, and inside that tank we had some N2, we had some O2, and now we're going to add some Z. Okay? What we just established is that adding the N2 and O2 together didn't alter the N2 or the O2, so I'm also going to further assume then that adding Z to it is not going to do anything weird. So, part A says, what is the partial pressure of the component gases? In other words, the N2, the O2, and the Z. Well, the N2 we knew. The N2, oh, let me write that as an actual pressure. Okay, the pressure of N2 before and after it was by itself, after it was in tank C with the oxygen, and now it's going to add Z on top, but we say that doesn't matter, so it's always going to be 0.78 atmospheres. I did that again. It's 0.73 atmospheres. The pressure of oxygen was 0.98 atmospheres. Okay, and now we're just adding some Z in there. And the Z, which they told us, come on, Kip. The pressure of Z, they told us, was 0.2 atmospheres. Alright, so those are the components of the mixture. Going on 9B. What is the total pressure? Show your work. Okay, you can show your work, but it's just addition. You're just adding them all up. Or if you want, you could say total pressure equals pressure of nitrogen plus pressure of oxygen plus pressure of Z, whatever Z is. So 0.73 plus 0.98 plus 0.20. So if that was 1.71 before, it's going to be 1.91 atmospheres now. And let's go to C. C says this chemistry student is performing this reaction in a tank and consumes all of the oxygen gas. Okay? Assuming the temperature and volume of the tank remain constant, determine the partial pressures of the remaining gases as well as the total pressure in the tank. Explain your answer. So, going back to our model here. Inside that tank, some student does a reaction that eliminates the oxygen gas or reacts with the oxygen gas, removing it as a gas. Maybe it sticks to a piece of copper and becomes copper oxide. Who knows? But no longer are the oxygen molecules bouncing around inside of the tank. So they are not exerting their pressure the way they used to. What does this mean for the nitrogen and what does this mean for the Z? Well, adding oxygen into the tank didn't affect the pressure of nitrogen and it didn't affect the pressure of Z. We're going to assume that taking it out also does not affect the pressure of nitrogen and it does not affect the pressure of the Z gas. So down here for part C, I'm going to say that the pressure of N2 is the same. It's still, and I'm going to get it right this time, 0.73 atmospheres. The pressure of the Z gas is still going to be 0.20 atmospheres. There just isn't any oxygen. So if you want to figure the total pressure is just add up the individual pressures, or the 0.73 plus the 0.20 should give you 0.93 atmospheres total pressure within the container. Okay. That's 9C. Let's go on to 10. Some practical application. A scuba tank contains a mixture of oxygen and helium. Before the dive, the partial pressure of O2, or oxygen, is 0.65, and the partial pressure of helium is 0.38. They call this a heliox mixture if you are a diver. What is the total pressure in the scuba tank before the dive? Okay. Total pressure in the tank, so we have 0.65 atmospheres of oxygen plus 0.38 atmospheres of helium, and together, what is that? 1.03 atmospheres of total pressure. That should be fairly straightforward. B, after the dive, the partial pressure due to the oxygen is reduced by 80%. Calculate the final pressure of oxygen in the tank. Okay, 80%. We can do this. We've got to take away whatever 80% of oxygen is. So oxygen was 0.65, and 80% of that is going to be 0.65 times 80 over 100, or 0.8. Okay, so let's do that first. In my calculator here. 0.65 times 0.8 equals 0.52. So that is 0.52 atmospheres is 80% of the oxygen in the tank. We have to get rid of that. Because if you read the problem, it says we lose 80% of the oxygen. Okay, it's consumed. So 0.65 minus 0.52, the original oxygen minus the amount of oxygen that was breathed up and used by this person, I assume, is going to be equal to 0.13. So that's how much oxygen is left in the tank, atmospheres. Calculate the final partial pressure. Good. If the total pressure in the scuba tank after the dive is 0.21, what is the partial pressure of helium? So that's part C. So we're going to say P total equals 0.21 atmospheres. And we just calculated up here that the partial pressure of O2 is 0.13. So now we have to find the partial pressure of helium. Don't forget, total pressure is going to be the oxygen plus the helium. So the total, which is 0.21, will be equal to the oxygen 0.13 plus whatever the helium is. So if I subtract the 0.13 from both sides, I get something like 0.8 So the partial 0.80 atmospheres is the partial pressure of helium. No, I did that wrong. 0.08. Okay. 0.08 atmospheres of helium remain in the tank. Okay, so again, there's no stop signs after this, which is so weird they didn't finish. So we'll go from, the next part is part 11 on to 13. It looks like there's just 3, so we have model 2. So go ahead and do 11 through 13, and then come back to the video. Okay, you should have completed 11 through 13. If not, go back and do that now. 11 says, consider the information in Model 2. Discuss with your group how you might illustrate air as a mixture of molecules in the tank in Model 2. Draw a particulate illustration of air. Particulate meaning show the particles of air, in air. All right. This is going to be tough. I'm going to draw a big container so I have room for this. Okay, here's our tank. And this is just pure air as it exists. Now, what I'm looking at here is 78% of the air is nitrogen. So if I make 100 molecules inside of this tank, 78 of them will be nitrogen. I've got to be kind of careful about that, though, because if you look down, 78 would be nitrogen, 21, if we round that number, 21 of them would be oxygen, 1 of them would be argon, and that would make 100 molecules, then I would have less than that, or 0 molecules of CO2. So to really do this properly, I would need something like, oh gosh, I would probably need not 100 molecules, maybe 10,000, if I wanted to get down and really show that there was some carbon dioxide in there. So that may not be realistic in your drawing. I don't know. I'm going to say, draw 10,000 molecules. Don't worry about that. But let's start with some. Definitely, most of this is nitrogen. Another way to do this, so if I color these in dark, because the nitrogen was dark, okay? If I make, let's see, this is like half the tank here, so halfway more would be 3/4. So basically, all this portion would be filled with nitrogen. Now, obviously, if you mix gases in a tank, they don't cluster at one end. It's not like all the nitrogens separate to one side and all the oxygens separate to another. That's not how this goes. But for the ease of demonstrating this, I'll go ahead and draw it like this. Understand that they would mix. Gases will always mix like that. Okay, here we go. Without some force that's separating them, I guess. So the top 3/4, a little more than 3/4 of this tank are going to be nitrogen. The bottom of this tank, the bottom 1/4, is mostly oxygen. Actually, closer to the bottom 1/5. So most of this is going to be oxygen, and the oxygens are clear. So we'll draw oxygen like this. Okay. I can draw them. And realistically, this is what your air is. It's mostly nitrogen and oxygen. Almost 1% of it is argon. So we could put a little argon in there. Argon is not diatomic. It's got little freckles on it. Maybe one of those is argon. And then there's some carbon dioxide. Some little tiny carbon dioxide. But it's so small. There's not much of it. Almost I can't draw it because it's so small. And now, representative-wise, I did draw 1 carbon dioxide and 1 argon. But if you're looking at that, that's 93-3, about. So it's almost 1/100. Maybe 1/30 is better. So a 30th. There are 30 times as many argons as there are CO2s. So this is much more present in our atmosphere than this one is. But for such a small space and having to do this by hand, that's not a bad drawing of what the air looks like. Now, if you really want to do this, jumble all those molecules together. And maybe I should draw more nitrogens in here so they don't look like they're so far apart. But essentially, this is the air you're breathing. This is the part we like because we use it. And then there's a lot of filler. It's mostly filler, stuff that your body can't use or can't access from the air anyway. You can use nitrogen, but you can't absorb it by breathing. Okay, that's number 11. Did it ask to draw just drawing? Okay, just draw. 12. Let's do 12. Looking at 12, on a particular day, the air pressure in the chemistry lab is 1.137 atmospheres. Discuss how you might perform the following calculations, and then do them. Show your work so that you can refer back to these calculations later. What is the partial pressure of oxygen in the room on that day? That's A. Here we go. Partial pressure of oxygen. Well, check it out. Here was our oxygen bit. No matter how big this container is, right, or how much pressure there is, this is always, this is always our ratio, okay, for dry air. We'll assume that it doesn't fluctuate too much. And our dry air, the O2 content is 20. Let's look at the exact 20.948% O2. That's how much oxygen there is. Cool. And the other thing we can think about is that all of those gas particles inside press against the walls and add to the total pressure. And remember, we kind of looked at this in the partial pressure up above. Okay? When we look at partial pressure, it doesn't matter which gas is which. They all add up. They all add up to the total. So if you pictured, let's go back down to our drawing. If you picture this, let's say that this was just at 1 atmosphere, that the total pressure inside of there from all the gases was 1 atmosphere. Okay? But 20.948% of those gases was oxygen. You could say that it was probably the partial pressure would be 20.948% of the total pressure. In other words, you would have about 0.20948 atmospheres of oxygen in a 1 atmosphere container. If it was a 100 atmosphere container, you would say it was 20. 0.948 atmospheres of oxygen, because that's 20.948%. So the percent, you can just multiply that by the partial pressure. So let's see here, or by the total pressure, excuse me. So the total pressure in this part, in this container up here, is going to be 1.137 atmospheres. That's all the gases together. What is the partial pressure of oxygen? Just multiply that by 20.948%, or 0.20948. Okay, so let's do that in the old calculator. We have 1.137 times 0.20948 equal, I get 0.2382 atmospheres, which is fine. Partial pressure of oxygen. B, 12b, how many moles of oxygen would be in a 10-liter sample of air from the room on that day, assuming the temperature is 22 Celsius? Show your work. Looks like an ideal gas law equation. So pressure, total pressure, should be, oh, excuse me, no, we have the pressure. The pressure of oxygen was this. That was the partial pressure of just the oxygen. So we had 0.2382 atmospheres of oxygen. The volume, they tell me, is 10 liters, equal to the number of moles. That's what we're trying to find. R is, come on, 0.0821 liter atmosphere Kelvin mole. Then they give me 22 Celsius. Oops, 22. That's not Kelvin, so I've got to add 273 to that, which looks like it's going to be 295. So 295 Kelvin. Okay. All right, I want to solve for n, so I've got to divide everything that's multiplying n, so I will get something like 0.2382 times 10 divided by 0.0821 and also divided by 295. Let's do that. So 0.2382 times 10 divided by 0.0821 divided by 295 in the calculator. The calculator is telling me I should have 0.09835. I'll just round that to 98. 98 moles of oxygen. That should be 12B. Going on to 13. 13 says a student wants to burn a 1 gram sample of ethanol in a jar containing air, assuming the air in the jar is at standard pressure and temperature, which is 22 Celsius. They say standard atmospheric pressure and room temperature. So don't assume this is STP. It's standard pressure, but it's not standard temperature. It's at room temperature, which is a little higher than standard, which is 22. What volume will the jar need to be in order to hold enough oxygen for the complete combustion? Ooh. This is a rough one. Okay, but they break it into parts. A, write a balanced chemical equation for the combustion of ethanol. Remember, combustion is reacting with oxygen. So we have ethanol, C2H5OH plus O2 turns into CO2 and H2O. Okay, that's fun. I see oxygen in two places. I'm going to balance the oxygens last. I will do the hydrogens first, I think. So it looks like I have 6 hydrogens here. So I'm going to put a 3 there and make that 6. I have 2 carbons here. I need a 2 there. That gives me... Alright, now let's count oxygens. On the left, I should have 3 oxygens on the left. On the right, I have 7. So if I put a 3 here, I should have 7 oxygens on the left as well. Okay, so that looks like a good balanced equation. Alright, that's A. Calculate the moles of oxygen needed to completely combust the ethanol. Alright, stoichiometry time. 1 gram of ethanol, C2H5OH, times, I want to get rid of grams of ethanol. I'm going to abbreviate ethanol as ETOH just to save space. And I'm going to go to moles, ETOH. And I know 1 mole of this, let's look that up. 2 carbons, 24, plus 6 hydrogens is 6, so that's 30, plus the 16 of oxygen is 46. So that's 46 grams of ethanol. Okay, times, and it looks like it takes 3 moles of oxygen for every mole of ethanol. So it's going to be 3 of these to 1 of these. That's O2s to ETOHs. Times, and I got to, does it say gram? No, it just needs moles of oxygen, actually, so I'm putting an equal sign there. Alright. Well, that's not as bad as it looks, because there's a lot of 1s in here. 1 times 3 over 1 times 46, so it's just 3 over 46. Let's put that in the calculator. 3 divided by 46. Okay. So, that is come on there. We're going to get a 0.0652 moles of oxygen. Moving on. C, calculate the partial pressure of oxygen in the jar. Well, we now have the moles. And the problem gave us the temperature and the pressure. No. Did it? It gave us standard pressure, yes. It did give us temperature and moles. Good question. Oh, we don't actually... sorry, I was thinking this was a PV-nRT problem. It is not. It is a partial pressure problem. So the total pressure... Oh, no, excuse me. Ignore me. We know the partial pressure of oxygen. It's 20.9... Make sure I get this right. 948. It is 20.948% of the total pressure. Well, the total pressure is, they said standard pressure, and standard pressure is 1 atmosphere. So if I want the partial pressure of oxygen, it's going to be 20.948% of that. Okay, so 1 atmosphere times 0.20948, don't even need a calculator, is 0.20948. Okay, atmospheres. Write that down here where I have more room. 0.20948 atmospheres is the partial pressure of O2. Pressure O2. Okay, got it. And last, so that's part C, and then part D wants you to put it all together. So I have moles, I have pressure, I have temperature. The temperature they gave me was room temperature, which was 22 Celsius, which we know, because we calculated it earlier, is 295 Kelvin. So I have those three, moles, temperature, and pressure. Now I can do an ideal gas equation, because what they really asked is what volume, how big does the container need to be? So let's do that. So pressure times volume equals nRT. The pressure I calculated here is 0.20948 times the volume, which is what we're looking for. So we equal to the moles, and the moles were up here, 0.0652. 0.0652 times the gas constant, which is always 0.0821 liter atmosphere Kelvin moles, and then 295 Kelvin. And I want to get volumes. I'm going to divide by this on both sides, 0.20948. So my final value, according to my calculator, is 0.0652 times 0.0821 times 295 divided by 0.20948 equal, I get 7.5, is that right? One more sig fig, 7.54 liters. Let's try to make sense of that in a real way, because that was a lot of math, but I want you to see what they're talking about. So essentially, we have a big container that we're going to pour some ethanol in. So here's a little puddle of ethanol at the bottom, a little alcohol, okay? And I want to burn it. Now these are all molecules. These are little ethanol molecules, okay? I'll draw them as little dots, all flowing around each other in this liquid. Each of those molecules takes 3 oxygen molecules. We saw that when we balanced the equation. So for every point down here, I need 3 oxygen particles floating around inside the container. So I need a big enough container that they will all fit in there at that pressure and temperature. And we calculated that in order to have a container big enough for those oxygen molecules, it needs to be a 7.54 liter container. Keeping in mind that not all the air in that container, if we just fill this container with air, it's not pure oxygen. Remember, only like this portion at the bottom, relatively speaking, is oxygen. Most of it up here is nitrogen. So we need a big container to get enough oxygen to burn all that ethanol. All right, so you're now up to the point where it says Model 3, collecting gases over water. Go through that section all the way to problem 19, and then come back to watch the video for that section, 14 through 19. Okay, we should have finished 14 through 19. We're looking at Model 3. According to Model 3, what gas is being produced by the reaction in the sidearm flask? Okay, in the sidearm flask, it looks like they have vinegar, Alka-Seltzer coming together. They cap it, and then look where it goes. It bubbles up out of there through the tube that's attached to the sidearm and collects in the bottle. And what we see is carbon dioxide. So we're making a lot of CO2 is being produced. All right, number 15. Describe how the gas is being collected as it is produced in Model 3. And I think for this, I am going to have to draw this. Okay. So here's our flask. And right now it's open, and you've got this tube coming off of it. Okay, the tube is going through this container here, which is also open. Okay, and it comes up this way, and there's a liquid in there, and there's a jar. The tube goes up through there, and then there's a liquid level inside the jar itself, and then there's gas above it. And in here we had some liquid that was vinegar that we dumped an Alka-Seltzer in. If you've never done this, it bubbles like crazy. So there's a bunch of bubbles that go up, creating this gas, those CO2 bubbles. And to keep those bubbles, because if they just came out here, they could get out the top, so we close it off. We put a stopper in there to keep it from going there. Now the only other place, if I had drawn the stopper correctly, herp, let's just pretend the stopper doesn't block the exit tube. So now when the gas goes up, it hits the stopper, it can't go anywhere except through here, and it bubbles up into this section up here. And if you notice the before and after, or sorry, the before reaction and the during, this level has changed. The level of gas inside has changed in the collection bottle. The collection bottle has much more gas in it after because of the bubbles from the CO2. So that's how it's being collected. And once it bubbles up through here, it's stuck here because it can't get back out. There's water underneath it. On to 16. Assuming the gas collection bottle was initially completely filled with water. So this part right here, this part that I measured on the side, we're assuming that was 0 to begin with. There was no gas inside of the collection bottle. It was all water. Okay, we started with all water. What gases are present in the bottle after the reaction? Okay. So what is this? What is this section here? What are those gases? Well, definitely one of them is CO2. Always going to be, I mean, because we're bubbling CO2 up into it. That was the gas we were trying to collect. But there's always another gas when you do it this way. We're assuming that this liquid here, that's inside of this collection chamber, that liquid is water. And water evaporates. Any water when there's space above it, it's just going to, some of the water evaporates. Try it. Leave a glass of water out on the table and wait several hours, and you will have less water in there because the water molecules, start to bounce around and leave the solution. So not only is there CO2 in here, there's going to be some evaporated water molecules bouncing off gaseous water. So we'll have water vapor, H2O gas. All right. That's 16. Let's go on to 17. Consider what we wrote down there on 16. Write a mathematical equation to show how the total pressure inside the bottle might be calculated using partial gas pressures. Well, we know our total equation. It's the total pressure is sum up all the gases. Well, the gases in this case, there's some CO2. So all the CO2 bouncing around up there is going to exert pressure, and so is all of the water. Any water that evaporates is now a gas and is bouncing around, so there's some H2O up there as well. If you add how hard both of those are squeezing inside the collection bottle, you get the total pressure. 18. Let's do 18. A table. The vapor pressure of water is well known and dependent only on the temperature of the liquid water sample. What this means is, if you have a sample of water, liquid water, and you look above it, because we know the water is going to evaporate, that will have a certain partial pressure. It will squeeze with a certain force. And it's at a certain temperature, that force is always the same. So what they've shown in this table is that at 20 degrees, if the water temperature happens to be 20 degrees, then the pressure of water above it, the part that's evaporated, will always squeeze with 17.5 millimeters of mercury worth of pressure. That's all. If you heat the water to 24, then the evaporated water above it is now going to squeeze with a pressure of 22.4. So we will always know how much evaporated water should be above a given sample of water, or what partial pressure there should be. Okay, so let's go 18A. Use the table above to determine the vapor pressure, which is the same as the partial pressure of water in the gas collecting bottle, and then convert the value to atmospheres. So, two things there. We need to know the temperature of the gas collection bottle, so let's look there. Does it give us a temperature? It does. If you look, the water is at 23 Celsius. So 23 Celsius, if I look on the table, 23 Celsius gives us a vapor pressure, or a partial pressure, of 21.1 atmospheres. Okay, 21.1 atmospheres, which we're going to say is the pressure of H2O in the bottle at that point. Oh, I made a boo-boo. That's not atmospheres. That 21 atmospheres. That would be huge. That's actually millimeters of mercury. Okay. We want it to be an atmosphere, so let's do that. 21.1 millimeters of mercury times, let's get rid of millimeters of mercury and get atmospheres. We know 1 atmosphere is 760 millimeters of mercury. So I just need to do 21.1 and divide it by 760. So, calculator time, 21.1 divided by 760 equals, not much, 0.0278 atmospheres of water vapor. Very little. Okay. Part B, 18B, says, if the atmospheric pressure in the lab and in the bottle is 0.989 atmospheres, what is the partial pressure? So when they say the atmospheric pressure, they mean the total. Total pressure in the bottle is 0.989 atmospheres. But remember, this is also true. The total pressure is equal to the CO2 plus the H2O. So let's do all that together. So the total pressure of 0.989 atmospheres should be equal to the sum. So we have the CO2, which we don't know, plus the water, which we just calculated, was 0.0278. All right, subtract that from both sides. And let's figure out what that is. 99 minus 0.0278 is, let's make some more room here. So the pressure, the partial pressure of the CO2 is 0.9612 atmospheres. So when I did this, all the CO2 that bubbled up here and got stuck in the bottle is pressing outward against it, and we can say that it's pressing outward with a pressure of 0.9612 atmospheres. So far, so good. Part C, how many moles of gas would be collected if the volume of the bottle is a liter? Alright, sounds like this has become a PV-nRT problem. So this is C, PV equals nRT. We know the pressure of CO2. Make sure I'm doing that right. Yes, is 0.9612 atmospheres. The volume, they told us the volume is 1 liter, equal to the number of moles, which we are looking for, times the gas constant, which is 0.0821, times the temperature in Kelvin. Now, the only temperature they gave us is the water at 23 Celsius. But the water is in contact with the gas, and the CO2 has been bubbling through the water. We are going to make the assumption that the CO2 is also 23 Celsius. But don't forget to make that Kelvin. So this is 296 Kelvin. Okay, 296 Kelvin. And we want N, so we're going to divide by these guys. And we're going to get 0.0821 here and 296 here. All right, calculator, let's do your thing. 0.9612 times 1, divide by 0.0821, divide by 296, and I get number of moles is 0.0396 moles of CO2, and which is how much we collected. So, pretty useful calculation. All right. And 19, would Dalton's law is the pressure total equals all the individual subpressures. Would Dalton's law hold true if two of the gases in the mixture reacted with each other to form a gaseous product? Discuss this in your group and be prepared to justify your answer. Tricky question. I will try to draw this one. I think this needs a drawing. If two of the gases combined and formed another gas, would it affect the partial pressure? Okay, let's make two gases, circle and triangle. So I've got a bunch of these floating around. Let's say that they combine together and they form square. What I'm looking at right now is a total pressure. I'm just going to assume each drawing is worth 1 mole. So I have a pressure total of 6. Well, there's 6 moles. Let's say that one of those is worth an atmosphere. So let's say this is a 6 atmosphere of pressure container. 3 from the circle, 3 from the triangle. Now, I'm going to react them. Let's say that this guy gets together with this guy, and they form a square. So I'm going to erase them. Where's my eraser? Here's my eraser. I'm going to erase them. And now they are a square. Now look. The total pressure inside is only 5 atmospheres. So this depends entirely on balancing chemical equations, because sometimes you'll get gas products that come together and form more gases than they used to have, and sometimes they'll come together and form fewer gases. For instance, if we go up here, let's look at the ethanol, the burning of the ethanol, if I can find that one. Here was our equation for burning ethanol. We had 3 moles of oxygen on the left. Ethanol, of course, is a liquid, so we're not going to consider it as a gas for just right now for the purposes of this. And on the other side, let's assume water is also a liquid, and then we'll assume that CO2 is a gas. It works if they are not, but for now, let's just make that assumption. So we are going, and here's oxygen gas. We have 3 moles of oxygen gas reacting to form 2 moles of CO2 gas. We're going from more gas to less gas. Sometimes that happens. Sometimes you go from less gas to more gas. I mean, this particular reaction is not an example, but there are some times where you start with 2 moles of gas, you end with 4 moles of gas. So in that sense, you're creating more pressure every time the reaction happens, and sometimes it's even. Whatever you start with is whatever you end with. So the answer to this question is completely dependent on the chemical reaction. So when it asks, would Dalton's law hold true if 2 of the gases in the mixture reacted to form a gaseous product? No, if it's going from 2 moles of gas to 1 mole of gas, no, you are losing pressure. If you're going from 2 moles of gas to 2 moles of gas, you are maintaining the same pressure. If you are going from 2 moles of gas to like 5 moles of gas, you are increasing pressure because you're making more gas particles. That's how this is going to play out. All right, almost done. Last bit is 20 through 23. Dive into that and then come back and watch this video. Okay, you should have finished the whole POGIL. We're looking at problem number 20. Consider the tank of gas illustrated in model 4. What is the total pressure in the tank? All right, well, we're just going to add up all the partial pressures. So the pressure total, that was not a letter. The pressure total equals, I have a partial pressure of helium of 0.35, plus a partial pressure of argon at 0.70, plus a partial pressure of krypton at 1.75. Add all those together, that's 1.05 plus 1.9, so 1.8, looks like 1.80 atmospheres is the total pressure inside the tank. Okay. According to Model 4, what is the symbol for mole fraction? I'm just reading it right off the table. We said mole fraction is x sub I. Easy. 22. Use the data in Model 4 to derive a mathematical equation for the mole fraction. Brainstorm possible equations with your group and divide the work to check each idea. When you think you have the correct equation, check to see that it can be used to successfully calculate all 3 mole fractions. All right. Immediately what comes to my mind is the fraction of all the moles there are inside of that. So I would need to know the total moles. So let's look at that. I have 0.1 moles of helium and 0.2 moles of argon and 0.5 moles of krypton. And if I add all of those together, I get 0.8 moles total. That's all the moles of gas inside. So that's like the total moles. Now let's do a fraction of that. Let's take the fraction of helium inside. So helium was equal to 0.1 moles. Now if we do the fraction of helium over the total, I would get 0.1 over 0.8. Let's see what the calculator says that is. 0.1 over 0.8 equals 0.125. Way. That's exactly what the table says the mole fraction of helium is. Argon. Let's look at argon. Argon had a mole fraction of 0.2. Well, we know the total was 0.8. 0.2 over 0.8, you can do that in your head. That's 1/4, or 0.25. And sure enough, 0.250 is the number they gave us. So what I'm seeing here is that the mole fraction is it's almost exactly like the partial pressure. If partial pressure is how much pressure each of those is giving out of the total pressure, then the mole fraction is it's almost like a percent of the moles. Or, is that right? Yeah, this is like a percent. It's like the percent of the moles of the entire container. So, let's say this. We can say the x sub I is equal to the moles of some gas. How are we going to represent gas? Let's say the moles of X, gas X. Gas X, okay. Divided by the total moles of all the gases. That's the mole fraction. Easy, 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 easy. So let's go to 23. The mole fraction of gas Xi can be used with the total pressure of the gas, pressure total, to calculate the partial pressure of the gas P sub I. Derive a mathematical equation for this relationship and check to see that it works using your answer in question 20 and the data in Model 4. Let's break that down. That's a lot of stuff. The mole fraction can be used with the total pressure of the gas mixture. Pressure total. So this is my interpretation of that. I should be able to get the exact same answer if I did this calculation, but instead of using moles, I use pressures. Let's try that. Helium. The helium partial pressure was 0.35. The total pressure, I have to add all of those together, was 2.8. Oh, did I do that wrong before? I'm such a goober. Everybody's thinking, why did I get this problem wrong? Or why is Mr. Gibb an idiot? All right. There's the real total pressure. 2.8. Okay. So the total pressure is 2.8. Let's see what the calculator says that is. 0.35 divided by 2.8. Lo and behold, 0.125. Which is exactly the same as the mole fraction of helium. So mole fraction and pressure fraction or pressure percentage, you could say, is exactly the same thing. So moles and pressure are almost can be used interchangeably for gases only. Is kind of the takeaway from this. So derive the mathematical relationship. Well, that is the partial pressure of let's do this for gas X. Not helium in this case. Oh, come on. So the partial pressure of X divided by the total, PT, let's do it for real, divided by the total pressure should equal X sub I. The same mole fraction. There you go. And now you finished the partial pressure worksheet.